Welcome to Paris class number 128, and today we're talking about real-world testing of flow control structures for a car, so a race car going around a track, these different aerodynamic features. And this is the third and final part of this three-part podcast series. The other two parts, podcasts number 126 and 127, we looked at some CFD results of these aerodynamic control devices. And to do that, we looked at a paper called Influence of the Car Movable Aerodynamic Elements on Fast Road Car Cornering. And this is an access paper. You can find it in the link in the description. So let's quickly recap actually what we looked at, because there are a few elements that we'll be covering in this podcast that come from that podcast. So in particular, a few of the different flow control devices. One of them is the rear wing, and for the most part, it is a very normal rear wing that you'd find on regular cars. However, the rear wing they have, you can rotate, so you can not only change the angle of attack, but you can also change, like tilt it from one side to the other. So like the left side of the wing is actually closer to the car or further away than the right side. You can see that in figure 17. And if you are listening to this on Spotify or Google Play or whatever, you can also watch the video on Spotify and or our YouTube channel. And on our YouTube channel, you can see other goodies as well, which I'm sure you'll enjoy. So the first aerodynamic flow control device that we'll be looking at in real life testing is the the rear wing. And this can be rotated and also pitched, like tilted from one side to the other, so I guess rolled, you'd say. Then there's also a splitter plate, which is quite normal for racing cars. And then also a gurney flap. And if you're not familiar with the gurney flap, check out podcasts number 126 and 127. Effectively, it's just a little like extrusion at the back of a wing, like so that the trailing edge that pops up in this particular case. And this dramatically increases the performance of this wing. In podcast number 127, I was very impressed with how well it performed. It's such a small thing, but it made a major difference to the aerodynamics of the vehicle. So that's probably like the dark horse of this podcast series. So let's move on to this podcast here. And now we're going to be looking at a few different real-world tests. So in this one, they looked at 3 different ways of setting the car up. So they have all these different aerodynamic surfaces. They have the wing, they have the gurney flap, they have the splitter plate, and now they have either in the manual setup phase where they manually pitched each one of these things or set each one of these things up to what they wanted. They then had the second type, which is what's called presets of control for the whole set of surfaces. So in other words, they had each one of these surfaces and they had like different relationships to each other. So they say, okay, if the rear wing is at this angle of attack and this tilt angle, we will then put the gurney flap at this, or the splitter plate or whatever. And then the third one is automatic control, and this is pretty cool. So the automatic control was based on what the car is actually doing, so how it is performing around the track. Let's say you have different gyroscope and accelerometer, for example, on the car. You can tell how the car is pitching, rolling, yawing, and you can tell how much it's accelerating in different directions. From there, you can actually tell the control surfaces to move in a different way to optimize the performance of the car, which is not completely new, but it is quite new in terms of, it's quite novel still, I guess you would say. Not a lot of cars do this, so that's pretty cool. And the car that they were looking at was this supercar, effectively from this Polish company, they say, called Aerodynamic Automotive. And the car is called a Husarian. And it looks pretty cool. Like it looks definitely supercar-like. I haven't really seen this before. And to give you an idea of what it kind of looks like, I would say like it kind of fits in like the Lexus LFA kind of styling category. It doesn't look exactly the same, but you could say that it passes for like an LFA kind of look. So it definitely looks the bit. And in their test, they had a few different parts to it in their real life testing. They have first, they're on a airport runway, and they have, first of all, they accelerate the vehicle on the narrow axis to the runway. Then they make a left turn on the airport runway. They brake, turn around, and enter the narrow axis road, turning around at its end and making another pass. So they have a short little circuit here with straights and corners of different radius of curvatures, and that allows the car to perform at different situations, so they can tell how well the aerodynamic components are performing. So this is a 2-door coupe, and it features a rear-wheel drive It has a lot of carbon fiber components. Under the hood, they say it has a 6.2 litre Chevrolet 8.8 cylinder engine, which gives 650 horsepower and 820 newton meters of torque. The acceleration from 0 to 100 is 3.2 seconds, so that's pretty quick. And from 0 to 200 seconds is 8.9 seconds, and then the top speed is electronically limited to 340 kilometers per hour. And thanks to the use of special steel, they don't say what type of steel this is, but special steel in general, the body weight has been reduced to 1,250 kilometers. 1,250 kilograms, not kilometers. So, as I mentioned, the different aerodynamic components that they are looking at is a front splitter plate. They're looking at a rear wing, which can tilt from one side to the other by 9 degrees. And it can also be pitched at up to an angle of attack of 60 degrees. So that's really high. And there's also a gurney flap on the back. And in figure 32, we see two different situations. They have what they call the maximum aero setup. And in the bottom figure is a minimum aero setup. So the maximum aero setup, they have the rear wing with a minimum angle of attack. They also have, over the maximum angle of attack and an inclination of 9 degree tilt angle, So it's tilted from one side at 9 degrees, and I guess up to a 60 degree angle of attack. Oh no, here it says 23 degrees. So I'm not sure what the 60 degree angle of attack would refer to, because the maximum aero setup only goes up to 23 degrees. So that's a bit strange. Anyway, so the wing is tilted at 9 degrees, angle of attack for 23 degrees, and the support plate is set at 40 degrees behind the wing. So the support plate, which we were talking about in podcasts numbered 126 and 127, is also called a booster plate. And this is effectively just like an additional little plate behind the wing that pops up, which greatly improves the the downforce under certain situations, but also the drag. So in cornering, if you want to like greatly brake, then you can pop this thing up, increase the drag of the car by like 50%, just this tiny little thing, or not even, maybe 30%, and then you can reduce the velocity of the car much quicker. In the minimum aero setup, the rear wing is not pitched at any angle of attack. It's just that it's like regular 0 degree angle of attack, but because it's curved, it's cambered, there is effectively downforce still being produced. There is also no support plate, so this booster plate is not on, and it's like put down, and the gurney flap is also put down. Whereas in the maximum aero setup, the gurney flap is definitely pitched up, so that's activated. So those are two different situations that they'll be looking at in this paper. They report these two different ones. So after they ran this car around the track, they looked at the lateral g-forces and the longitudinal g-forces. So in other words, the longitudinal g-forces is like in the driving direction, whereas the lateral g-forces are from side to side. And they have this plot here in figure 35 showing the g-forces pulled in the minimum aero setup and in the maximum aero setup. And it's pretty cool. So overall, the longitudinal g-forces don't really change too much. Like for the minimum aero setup, the greatest g-forces that it was pulling in the longitudinal direction were like minus 0.5 to 0.35 perhaps. In the maximum aero setup, there's a little bit of an increase, like it's minus 0.6 to 0.5, so maybe a 10%, 20% increase there. But the lateral g-forces is really where the aerodynamic setup has a big difference. So for the minimum aero setup, the g-forces pulled are from minus 1 to about 0.6. But for the maximum aero setup, they're getting g-forces all the way to like minus 1.3 all the way to 0.75. So that's like 50% increase, or maybe 30% increase either way. So the maximum aero setup really benefits the lateral g-forces a lot more than the longitudinal g-forces, it seems. So what does this mean? It means that the car can go around corners much quicker because the g-forces it can pull from side to side are greater. And also the longitudinal g-forces are greater, so it means it can accelerate and brake a little bit quicker, which is to be expected. But the lateral g-forces definitely do seem to be where these flow control devices come into their prime. So that's the general g-forces pulled by the car throughout this test. What about with different velocities? So figure 36, they plot this. So they have a few different aero setups. They have the minimum aero setup, the maximum aero setup, and now the aero setup with only the wing. And with the minimum aero setup, well, first of all, the maximum aero setup allows the car to travel at much greater speeds around corners. We can see that where about the same lateral G's are pulled, but they are pulled at much higher velocities with this maximum aero setup. So like with the minimum aero setup, the maximum G's pulled are like 0.6 perhaps in the lateral direction. With the maximum aero setup, okay, the G forces pulled are a bit greater, they're about 0.75, but they also are pulled at a much higher velocity at like 23 meters per second instead of 19 meters per second. So this maximum aero setup allows the car to go around corners much quicker. What's more, the maximum velocity that is shown here is greater for the Aero Max setup. So in other words, with the maximum aero setup, the car could go around corners faster, showing that at some points it was going around corners at about 37 meters per second. Perhaps that's a straight and braking into corners, whereas for the minimum aero setup, the maximum velocity that this car was able to go at was like 32 meters per second, so like 12-13% less velocity. With only the wing though, this is interesting. So with just the wing, the advantages that the entire max aero setup achieved is kind of halved. So with just the wing, the performance of the entire car kind of lies between just the minimum aero setup and the maximum aero setup, which is interesting because the wing is only just one part of this entire aerodynamic package. You have not only the wing, the gurney flap, the booster plate, and the splitter plate. So there are 4 different elements here. And sure, the booster plate and the gurney flap do interact with the rear wing, but still the booster plate by itself you'd think would have quite a big effect, as would the splitter plate. But all of them together really only double the effect of just the wing itself. So it's like the wing is making up for half of this advantage that the maximum aero setup is producing. So with just the wing, the velocity that the car could travel at up to was about 34 meters per second, and it was pulling G's at about 0.7, the maximum lateral G's. So another thing that should be mentioned is that the braking definitely improved with the Aero Max setup. So the maximum, or I should say, the greatest negative lateral G's pulled was far greater for the Max Aero setup, so it was like 1.3 perhaps, whereas for the minimum aero setup, the maximum G's was only -1. So again, there's about a 30% increase in the lateral G's that this setup could allow the car to pull. So they say, reading from this graph, the maximum speeds corresponding to the accelerations of the adhesion limits of the tires, the following values are obtained. So what is the adhesion limit of the tire? It just means how fast can you go before you lose traction and you spin out, or you lose you have some sort of slide slip, like you don't get full traction on the car, on the road. So the aerodynamic elements set to the minimum speed of 31.6 meters per second. So this was for the minimum aero setup. They could only achieve this speed of 31.6 meters per second. Using just the wing, the car could get up to 33 meters per second, they say here, which increased the maximum this speed by 4%. Using the wing, the underbody support plate, and the gurney flap, the velocity that this car could now reach was 36 meters per second, which is a 30% increase in the speed relative to the reference speed. So in other words, they said here, the car can travel at 30% faster velocities effectively when you're in the Aero Max setup compared to the minimum aero setup. And the situation described suggests a greater safety of margin can be achieved by activating the moving aerodynamic elements. So that means that you can run the car faster and still have, or at the same speed, and have a greater safety margin so you don't spin out as quickly. So in conclusion, let's talk about what we found with all of these podcasts, from the different aerodynamic elements to this on-road real-life test. The first one is, a wing positioned obliquely at the rear of the car responds poorly to the flow asymmetry caused by the vehicle's curved motion, so going around a corner. The generated lateral force is less than expected. The aerodynamic downforce is slightly reduced. And this was a big surprise to me as well. So when you have a car going around a corner and you have this rear wing and you tilt it to one side, I would have thought that a lot greater lateral force would be produced than what it was produced. They found that it was like 250 newtons or something for such a massive wing at 9 degree tilt angle. And that resulted in almost no benefit to the car. It was not that much, it's like 25 kilos of side force effectively. And they said here that the aerodynamic downforce was slightly reduced as a result as well. So that's not good. It means that you can't really get as much traction, which would also potentially reduce the speed that you can go around the corner anyway. Second conclusion is that a very effective movable aerodynamic element is the booster plate placed under the wing, improving its flow and aerodynamic characteristics at high angles of attack. Such a role seems to be fulfilled by the lower wing in the Bugatti Veyron. So this is the booster plate I was talking about. How it is not that big a surface, but it definitely increased the drag of the vehicle by like 30% and even the downforce by a considerable amount up to a certain angle of attack. Once you went past that, then problems occurred with the interaction of that and the actual wing itself. So there's a sweet spot there. The third conclusion is that movable aerodynamic elements placed behind the axis of the rear wheels play the role of elements that increase the downforce on the rear wheels, but at the same time reduce the downforce on the front wheels. So in other words, if you put flow control devices at the back of the car is going to get affected. And what this does is it shifts the balance of the car front or back, depending on how much you put and whether you put them at the front or at the back. So this can potentially be good, but if you need like a certain stability, like a certain distribution of forces from front axle to rear axle, changing that could then result in instability to the car, which means that the handling reduces, and it means you can't go around corners as fast, and it means that you have a slower time. The fourth conclusion is that the splitter plate under the front part of the body partly balances the car aerodynamically by relieving the pressure on the front axle. The fifth conclusion is that the data contained in works from references 18 and 19 show that the shortest times on racetracks are obtained from rear axle aerodynamic loads within 55 to 70% of the total downforce. So in other words, loading the rear axle more than the front axle will give you better times around tracks, generally speaking, than loading the front axle more. And that ratio is about 55% to 70%. And movable aerodynamic elements allow dynamic adjustment of this downforce so you can stay in that sweet spot as you go around different corners. Large ranges of rear wheel downforce change allows for aerodynamic balancing of dynamic front wheel loading during sudden braking. So in other words, when you brake suddenly, a tendency is for the car to like lurch forward because you're like compressing the suspension on the front. It depends how stiff the suspension is, but if it's quite soft and even if it's somewhat hard, you'll still get a little bit of like play forward, and that actually lowers the front axle a little bit more and also changes effectively the angle of attack of the car. So the car is like tilted forward a little bit, which does change its aerodynamic performance a little bit. By having these different aerodynamic components, you can change that and sort of alleviate that in real time. Now there's obviously a limit to that because you have these elements which have their own inertia and you can't really change them instantaneously. They do take time to respond, but that is like with automation, you can get a pretty decent reaction. The sixth conclusion from these podcasts is that test drives with a twisted rear wing through a test curve with a radius of 19 meters could be performed at speeds of 30% higher than without it. So in other words, we found just now that with this like body kit kind of thing, you could go around corners 30% faster than without it. So that's pretty sweet. And that's without losing grip as well. The seventh conclusion is the computational results showed that it is difficult to obtain significant aerodynamic downforce for the front axles. The splitter plate located at the front under the body generates downforce, but its magnitude depends on its surface area. And the eighth conclusion is movable aerodynamic elements can change the aerodynamic characteristics of a car within a wide range, but they can be most effective when coupled with a GPS system with a programmed route, which would enable their predictive actuation. So that sort of blends into what I was saying before, where you have these aerodynamic elements which you can change, and you can like pitch them differently or tilt them or whatever, and it takes time to do that because they have their own inertia. So if you have like this GPS system, for example, with like a pre-programmed program in there saying like, okay, you're coming up to this corner, change these aerodynamic elements to this configuration, you can then take advantage of what you have. So those are the conclusions we have here, and that's in this podcast. And if you want to learn more about this kind of thing, you can also read this paper. There's a bit more information in here that we didn't cover, but we covered like all the important things, I think. So make sure to like, subscribe this if you liked it and you want to get more podcasts like this to you. And if you want to get better at CFD and or theory, check out our courses in the link description. And if you want to make your experiments 2 to 4% more accurate, check out the atmosphere Hawk. So the density of air changes every day by about 2 to 4%, and the atmosphere Hawk measures that for you. And between days, weeks, months, seasons, the density of air changes even more than that. So it can change up to 15% is quite normal between seasons. And if you're not measuring the density of air in your wind tunnel, then you're getting that error into your wind tunnel. And that's not good, because when you go back to your computer, you analyze your data, trying to find trends is going to be difficult because the error in your data is just engulfing everything. And in fact, some trends that you do find are not going to actually be real. So that's a problem. The atmosphere Hawk gets rid of that error for you, so you can trust your data. And if another problem with this is that if you don't measure the density of air, if you were to use your experimental data to validate your CFD, then obviously that's going to be problematic as well, because your CFD is using a certain density of air. You usually set it to like 1.2 kilograms per meter cubed or 1.225, but the problem is that your experimental data wasn't taken at that density. So you're trying to validate your CFD with experimental data which wasn't taken under the same conditions, which doesn't make sense. So that means that your CFD is going to be erroneous, and at best you're just going to have a flawed validation process. So the atmosphere Hawk gets rid of that error for you, makes your CFD more accurate as well, more trustworthy. Check that out in the description below, and I'll see you next podcast. Peace, amigos.